Okay, I think we can start. So good afternoon again, everybody, and welcome to this webinar on locomotion and navigation in harsh environments. This webinar is organized by the Robominer project. My name is Claudio Rossi, and I'm the coordinator of the project. Just to start, a few words about the project. Robominers respond to the EU call for the new solution for sustainable production of raw materials. And our vision is to bring the digital revolution to the raw material field, contributing to the transformation of the mining industry into a high-tech industry. One of the challenges we are facing is locomotion and navigation in this unconventional environment. And this challenge is faced also by other colleagues, by other projects. So the aim of today's webinar is to provide an overview of solutions being developed to allow robots moving in very strange environments, like mining underground, like in our case, but also artificial pipelines, and even on the moon. So we will have 4 presentations on heavy-duty robotics in flooded tunnels, robotic solution for exploring interesting places on the moon, miniature robots for buried pipes, and underground locomotion and navigation. I will introduce the speakers one by one before the presentation. And after each presentation, there will be a Q&A session where attendees will have the opportunity to ask some questions. And you can use the question and answer tab of Zoom to formulate your questions. Before we start, let me remind you that the session will be recorded, and an edited version of the recording will be publicly available on YouTube channel of the project in the next few days. The first speaker is Professor Jussi Aaltonen. Jussi is the research manager in the mechatronics research group of Tampere University in Finland. His research interests are aircraft engineering, autonomous systems, and general mechatronics engineering. Jussi will talk about sustainable heavy-duty robotics in flooded tunnels. So Jussi, when you're ready, the floor is yours.
Thank you, Claudio. As Claudio mentioned, my topic is sustainable heavy-duty robotics in flooded tunnels. First of all, let's take a look at what sustainability means. There is a general interpretation for sustainability given in so-called Brundtland Report 1987, and it means development that meets the needs of present without compromising the ability of future generations to meet their own needs. And what this means in terms of mining, of course, it means that we have to minimize the environmental footprint of the mining. And minimizing the environmental footprint of mining, of course, it happens in all the sectors related in mining all the time. And in this presentation, I will be really concentrating into the machinery, how we can make machinery more suitable for sustainable mining. So what does this all mean to mining machinery? Of course, if we think about operations the machinery does in mining in general, how to improve the sustainability. One way is to minimize the infrastructure required to operate the machinery. There is usually in the mine, there is huge infrastructure which is just supporting the operations in mine, ventilation, pumping, so on. One way is to minimize the waste, so that we excavate as little waste rock as possible, produce other waste as little as possible. Then, of course, minimizing the environmental risks. So, in general, not bringing into mine anything which causes some kind of environmental risks. This also means certain things in terms of machinery life cycle. we have to consider the life cycle more thoroughly. Think about the reconfigurability of the machinery, how the machinery of today can meet the needs of tomorrow. If our operation change, how we can change our machinery to meet new requirements. Reusability, when our machine is end of its usable life in our mine, what will happen next? Can it be reused somehow, and in what purpose it could be reused? Then finally, of course, recyclability. If the machinery can't be reconfigured, it can't be reused, then we have to recycle it, and that's the anyhow the final destiny of all the machinery is to become recycled. But then if you think about the machinery in itself, what's most important, of course, is low power consumption. Of course, if we think about mining, excavating the rock, we need certain power always. One ton of rock needs certain amount of energy to become to go out of the mine. But low power consumption, high efficiency, those are one keys to have sustainable machinery. Then low emissions. So of course, in the mine, those emissions, they are crucial. In traditional mine, emissions cause need to ventilate the mine more, and so on. So, but also in general, we want to produce as low emissions as possible, not only inside the mine. Environmentally safe technical solutions here, they are very important. Most of the modern machinery, they carry quite big amount of environmentally harmful fluids, for example, fuel, hydraulic oil, so on. One key thing here is also the small size. The smaller our machinery is, the smaller tunnels it needs, the smaller veins it could follow, the less waste rock it produces, and so on. How then to achieve the sustainable mining machinery? How can we make them more environmentally friendly? As I already said in the previous slide, of course, decreasing the size of machinery is one thing here. Decreasing the size is only possible, of course, to certain limits, because the key is anyhow to excavate the rock and the ore, and it requires certain size. Minimizing the power consumption, then using environmentally safe technologies, and also recyclable materials. Improving reconfigurability, this improves our machine life cycle, makes the machine life cycle longer, and improving also reusability of machines. And but anyhow, even though how environmentally friendly our machines are, they have to be able to mine profitably. And to increase the profitability of mining, our machinery, they should minimize also personal requirements in the mine, maximize the availability and reliability of the machinery, minimize the amount of waste rock produced, and so, in this Robominer project, we are developing one possibility for future mining machinery. we call it Robominer. Robominer is bio-inspired, modular, reconfigurable robotic miner. It is autonomous to minimize the personal requirements in the mine. The bio-inspiration in terms of Robominer, it means it's locomotion. So the locomotion principle of the Robominer is bio-inspired, but it also means the maneuvering of the robot, the production methods it uses, the sensing technologies it uses, and so on. Modularity, it begins from separating the functions and the capabilities of the robot and building the robot modular according to these. This also improves the possibility to reconfigure the robot for other possible uses. Robominer is also very suitable for sustainable mining applications. It produces no local emissions, so it doesn't produce emissions within the mine. Of course, it uses energy, and somewhere there is small emission because of that. It doesn't contain any harmful fluids. Its power consumption is very low. It doesn't need any support infrastructure, so it can operate underwater to very deep depths. So the mines don't need pumping. And of course, as mine is filled with water, it definitely doesn't need any ventilation either. If you think about the modularity of the Robominer, as I said, it's built modular by separating the functions and the capabilities of the Robominer. We can separate the miner into a couple of modules. It has production tool module, which has certain functions. It does the excavation or sensing, also takes part in locationing and mapping. Body module in the robot is the one containing the most of the systems of the robot, which are all built modular. Then it needs also support modules underground and also on the surface to support its operations underground. Robominer prototype, which we are building in this project, will be fully autonomous. It will have a quite novel Scrolllike locomotion system, which is bio-inspired, even though it might not seem that, but it actually follows the same locomotion principle than mud skippers locomotion is. It's built from independent modules which are either specialized or universal. So in this picture, in this slide, we have two body modules and the production tool module. Body module is one of those universal modules. We can connect as many body modules as we want together with these active joints, which is in between them. And production tool module is one of those specialized modules, which is only for certain purpose. Robominer will be capable to self-assemble and self-configure. Of course, self-assembling doesn't mean that we throw a bucket of nuts and bolts to the mine and they will organize themselves. But each of these larger modules, meaning body module, and so on. These are capable to organize as a complete robot for certain needs inside the mine. Also, it can change its configuration, so that, for example, changing the production tool or something by itself. It's capable to excavate a channel which is large enough for itself, and also it's capable to excavate to any direction. So 90 degrees down are possible. Of course, the turning radius of the tunnel is limited by the reach of the production tool module, and also the angle the active joint in between the body modules can reach. It's capable to move the cuttings. So as the production tool cuts the rock, this Robominer, it moves the cuttings through it to the transport system, which then moves the cuttings forwards. Also, it will be capable to follow ore veins, so it's capable of selective mining, and that way producing as little length of tunnels as possible. Our Robominer, it contains two power systems. There's water hydraulic powertrain, which is responsible of all the actuation, the locomotion, and also the production tool of robot. It will be running on pure tap water, so there is really no environmental risk related to the hydraulic system of this mining machine. It also is so-called open system, so there is no tank, and the fluid, meaning water, is not recirculated back, but the water is used for flushing the robot parts, so that robot is kept clean of debris, which improves also its reliability and lifetime in those conditions. The hydraulic power, which is only 35 kilowatts, it has intelligent power distribution, which helps us to minimize the peak power requirements of the robot, and that way maximize the production rate we can achieve with that power. Electric system has very low power. It's only about 300 watts. It's single voltage, so robot has only one 48-volt bus bar, which is supplying all the electric consumers in the robot. This is to improve its make it more simple, and that way improve its reliability. Also in electric system, as you can see, the power is very low, so we need that intelligent power distribution to minimize the peak power of the robot, and then enable all the electric equipment to work when needed. Electronics and communication system, it's in the robot, it's built as a distributed system, and it has intelligent independent modules which are not dependent on each other, which may make it very damage tolerant system, and also it's quite easy to build redundancy between the modules in that kind of system. Communications is based on wired and wireless Ethernet in the robot. So within the robot, as much wireless as possible. Interesting feature in this robot is that all the systems we have in the robot, they are pressure compensated, so which means that they work in full ambient pressure. This makes robots' structural components much lighter and easier to manufacture because they don't have to withstand the high ambient pressure in the deep water-filled mine. So far we have been able to get all the electronics needed in the robot to work up to almost 500 bar pressure, which means 5,000 meters depth. So going a little bit deeper to technical details, I'd like to present this Scrolllike locomotion, which is one of the novel features of the robot. It's based on quite well-known principle of screw locomotion. So this Archimedes screw type screws rotating against the surface. Vehicles using this locomotion principle, they have been around for almost 100 years. So in screw locomotion in itself, there is nothing new, and it's quite well known in principle. But combining the screw with the leg is the novelty in this one. Screw has certain benefits in comparison to tires or tracks, which are commonly used in mining machinery. Screw is simple, so it has one moving part, which makes it reliable. And especially machinery operating autonomously inside the mine without possibility for human intervention to the operation, this reliability and simplicity is a crucial thing to have a machinery which is available when it's needed. Another benefit in screw locomotion is that it enables robot to move to all directions. So as you saw in previous slide, our robot body modules, they have 4 screws, 2 touching the ground of the tunnel, 2 touching the wall of the tunnel. 4 screws make it possible to rotate the robot in the tunnel, turn it to all directions, drive sideways, and so on. Then why to add leg to the screw? First of all, it enables us to position the screw against the wall. So whatever way the wall is tilted, we can tilt the screw to same direction and have as large contact area as possible with the wall. Another benefit of the leg is that with this leg structure, our robot can walk. And as you can see on the picture's right side, we can move the screw unit back and forth, and we can also move it in and out from the body module. So there is limited possibility for the robot also to walk with these screws, which makes it possible for it to step over an obstacle, to place the screw on top of the obstacle and step over it. Then you can see in these pictures, you can see artificial hydraulic muscles. These artificial hydraulic muscles are the main type of actuator we are using in this robot for linear actuation. And artificial hydraulic muscle, it's not very common actuator. It's mostly or used only in pneumatic systems, not in hydraulic, and not commonly used, but it has certain benefits also. The biggest one is that it contains no moving parts, which then we from that we get benefits in damage tolerance of the hydraulic muscle. In operations like mining operations, the hydraulic cylinders, they usually break by getting hits to the cylinder rod or something like that. Artificial hydraulic muscle, it doesn't have cylinder rod, which can be damaged by hitting rock or something like that. So by using these artificial muscles, we improve the damage tolerance, and we improve also the reliability of the machine in general. The lower number of parts, the higher reliability always. The screws are driven by water hydraulic motors, and the return flow of the motor is used for flushing the screw structure, so that we don't get any debris stuck anywhere in the hydraulic muscle. And I guess I finished within the time, so now it's time for questions then. Thank you for your attention.
Yeah, thank you very much. Usually very interesting. So I have two questions here on the chat. The first one is, you said a smaller size means enhanced sustainability. Can you please tell us how small you think the Robominer machine can be, considering structural, locomotion, and hydraulic power constraints?
I can actually go back in slides. So in this slide, we have the size of a Robominer, rough size here. So with two body modules, the Robominer and the one production tool module, the length of Robominer is approximately 5 meters. Length of one body module is 1.5 meters, and the diameter is between 735 to 900 millimeters. So it depends on how far the legs are extended. Weight will be around 1.5 tons. So very lightweight mining machinery. And the production, of course, the production rate is related to the size of this machine.
Yes, just a comment from my side. It's going to be a small mining machine for the mining machinery scale, but it's going to be a huge robot for the robotic scale. Okay, so then we have another question. Did you consider other types of locomotion, like, for instance, peristaltic systems?
Yes, we considered actually quite many types of locomotion, but one key thing here is to minimize the number of moving parts in the locomotion, and make it as simple as possible. And that thought about making it as simple as possible led us to this screw locomotion idea. Also, one important feature in the locomotion is that with this type of combination of screw and leg mechanism, we can get very high reaction forces towards the tunnel walls, so we can accept higher forces from the production tool also during the production.
Okay, thank you very much, Jussi. We don't have more time now for questions, but there will be another slot at the end of the webinar. So if there's other questions to Jussi, we can take them later. So the next speaker, thank Jussi. The next speaker is Alexander Dettmann. Alexander received his diploma in electrical engineering from the University of Cooperative Education Ravensburg, and master and PhD in systems engineering from the University of Bremen. He's involved in several space-related projects as a researcher at the DFKI at the University of Bremen. And Alexander works on autonomous and mobile exploration robots and participated in the design and control of legged robots. He's currently leading the space robotics team at DFKI in Bremen, as well as the European project Robotic and the ESA project AND. Alexander will speak about robotic solution for exploring scientifically interesting places on the moon. So Alexander, when you're ready.
Yeah, thanks for the kind introduction. Yeah, now we make a large jump actually to the moon. So my talk is about robotic solutions for exploring scientifically interesting places. So the first question that we should address is why actually want we go to the moon? And there are like three major parts. So first of all, if we get more insights of the moon, we can analyze also and understand the genesis of our solar system and also of our own Earth. Yeah. And then, of course, there's always the question, are we alone in the universe or is there something else? And so it's always, one major driver is also to find signs for current or ancient life within our universe. And the last one is also for colonization. So there are actually plans to really build up habitats on the moon that also we provide there like factories to harvest the resources of the moon and to actually build products out there. But yeah, one major thing that we need to find in order to do this stuff, we need water. And this can be found in form of ice on the moon. And there are like one very prominent place is at craters, which are more located on the poles of the region. So one example is here the Shackleton crater, which is on the south pole of the moon. And this, as you see in the ESA artist drawing here, the vision is that we can build up here a habitat right next to the crater in a spot where we actually have permanently or almost permanently sun coming there to feed solar panels with power so we can generate energy. But right next to us, we have this crater, and due to the flat angle of sunlight on the pole region, this crater is permanently shadowed. And it means we have -degree all the time and a high potential source for finding water ice. So what we got to do is we have to get into the crater, harvest ice, and bring it back. And the other interesting places can be found more on the equatorial area. This is here below a picture from NASA from the Marius Hills region. This is a volcanic region, and there you have ancient lava tubes underneath the surface. And once in a while, there are very thin regions where the ceiling collapsed, and this looks like a skylight. That's how they call it. So they're very round and around like 50 to 60 meters in diameter. And it would be also very interesting to get in there to analyze the subsurface. And there are also very nice ideas of sealing this part down below here so that you can also create some kind of atmosphere. And this, of course, would make a habitat that lasts for longer times quite interesting. So, and in order to reach the scientific places with robotic systems, we have a lot of requirements on them. And one is, first of all, that we need to provide robust systems and that are capable to cover the demanding environments that you face on the moon. I come in the next slide also a little bit more into detail on that one, but you also, you need to be robust, but you also need to adapt to the different surrounding conditions. Then of course the robots, they should act as possible, autonomously as possible. And that means they have to localize and map their environment themselves, and also plan the next the missions or the next tasks that they're gonna do, and also the trajectories to get to certain points. And then, of course, manipulation is also an issue, because we just don't want to send robots out there to explore, but now in the next generation, we also will want to use them to prepare already infrastructure on the moon, so that when astronauts arrive, that they can find already some kind of infrastructure that can be used. And since we want to increase the efficiency of missions, a lot of missions consider already not just to send up a single system, but also multi-robot system that cooperatively act together. So talking about mobility, here you can see a lot of systems that we built in DFKI, because we say, okay, we have unknown environment with unstructured terrain. On the moon, you can find very, very fine sand, which is here called regolith, so it's like more like powder. But on the other hand, for example, if you go into the lava tube, there you find really sharp edges and rocks inside, and you have to accommodate for that. Then in order to get down this craters, you need to cover steep inclines, and you always have the possibility that you have some hidden pitfalls or some unconsolidated terrain, so that you need to react in real time on to these changes in the environment. And that's why we developed this multiple locomotion concepts. On the left-hand side here, where you see the video hopefully running smoothly, is the Artemis system. And as you see, it's very much close to the actual Mars rovers or Curiosity. So we have a passive suspension system, but which has very good possibility to adapt to the terrain. The more active approach would be here our Sherpa system. This one has like wheels on legs, and with that we have also the possibility to adjust the footprint. And with this you can come to, for example, here to very narrow passages, and in other passages you maybe want to have a more wide stance to increase the stability. So there are different pros and cons for different configurations that you can use. And of course, due to the legs, you can also overcome larger obstacles by just placing the foot on top of it. Then a more simple system, which is actually then easier to control and also more robust, would be then this Coyote system. And the prominent thing about this, as you see, are the star-shaped wheels. This is like legs on a wheel, but they also provide very good traction, especially in sandy terrain, but also, as you see in the video, when you come into very harsh environments, you also have a superior mobility. And then we have legged systems, as you see here on the right-hand side. So we have 6-legged walking systems, which provide an intrinsic stability already. But we also have like quadrupeds, which are a little bit more efficient. And also like things in between, like for example, this mantis robot. This one can move on 6 legs to provide a lot of stability, but it can also lift up its upper body to use its forearms for dual arm manipulation tasks. So this is a robot that is not just exploring, but also should help to build up infrastructure. Yeah, and due to the fact that we have delays in the control, I mean, if you consider Mars or something, but what the robots need to do is they have to react very, very shortly on any circumstances, and you want to reduce the intervention between the human and the robot as much as possible to make the mission more efficient. So that means you have to increase your autonomy, and here the DFKI, we're focusing on traversing extremely rough and inclined terrains. For example, here this is from the AND project, where we built up a navigation system for legged systems together with the partners from IIT. And here we're not just doing path planning as we do for rovers, but we also plan the paths in a way that we utilize actually this rocks on the path in order to increase our traction. So what we want to analyze is whether we can reach even higher slopes when we have obstacles in between, instead if we just have would have a plain surface. Yeah? So, but that also means this is a different kind of navigation that needs to be applied. So, and altogether, since we have this manifold robots, we also focus on have a robot-dependent exploration and path planning. Yeah? So not take the same planner, yes, maybe the same planner, but with different configurations, so that we get the full potential of this mobility of the system also on the trajectory. Yeah, simultaneous localization and mapping, I think it's clear. But here we also go like one step further, which you see in the pictures below here. Instead of just building up a map for navigation, what we also try in our current projects is that we build up a simulator out of it, a physical simulator that we can use first to internally simulate what the robot is going to do next. So we can try different passes to reach a certain goal. And then after we had this like more precise check of a certain path, then we actually just apply it on the system. And this of course increases then the safety and also the efficiency, because we are less prone to navigate to a dead end or something. And what is really important is, of course, that we do long distance traverses as well, so that we really test our systems. Here you have an example where we tested our shared binary U project in Morocco, in the desert of Morocco, and there we went like a whole day autonomous driving and managed to drive more than a kilometer autonomously. Yeah, and then, as I mentioned, just a single system is good, but if you have multiple of them, it gives you more potential, and therefore you have to also, of course, have to solve certain issues with the systems. But what we worked already on like a decade ago is to work on heterogeneous multi-robot systems. That means we want to place not systems of the same kind, but they should differ so that they can use for different aspects. For example, here we have the old Sherpa system on the left-hand side with the cracks underneath. And on the top, you see already our current design. And here it's working together with the Coyote system. And as you see, we have this like standardized interfaces, which provide mechanical connection, but also power and data. And by providing the standard interconnects, we can supply, for example, here the Coyote with a module. This can be a scientific payload. This can be an extra energy item, for example, to enlarge the distance that can travel. And with this system, you can build up also logistic chains. But therefore, of course, you have to take care about the mission planning and handling, so that you consider multiple robots and really see, okay, which robot has to go in which direction, how long does it take to get there, and to synchronize again. So these are questions we would like to answer, so that the system is doing this autonomously as possible. And with respect to the logistics chains, here are some pictures from our current project. Actually, this is the Robotic project. It's also a U project, where we actually have a multi-robot system that is first like generating a map of the surrounding of the skylight, and then actually we have the Coyote system that is repelling from the Sherpa into the skylight. So we want to go into Rang here. Therefore, we have a tether management and docking system that is doing the repelling, and as soon as we're there, we can undock and then start the exploration of the lava tube underneath the surface. We analyzed this already in a study here, and now we're going this into practice. And yeah, the last part would then be actually this cooperative manipulation. It's already a heavy task on Earth, but it's of course not easier on Moon. But if we have multiple systems there, they have high potential to cooperate together in order to, for example, unpack things from the lander, to build up here. This is an example of a 3D printer that is doing this in-source resource utilization. So it's using the granulate from the Moon in order to build up structures that can then be used later on for building up, for example, some kind of houses, or habitats. So that was about my presentation. Thanks for your attention. I think I'm now free for questions.
Thank you very much, Alexander. It's very interesting. We have time for a couple of questions. The first one is the following. If I understood well, we're seeking a compromise between a locomotion system that works well in hard rock and regolith. Have you considered having a system that would be using different modules or solution, perhaps with a common core system for different environments?
I think I did not get the last part of the question. So we're having the problem of having fine granulate and also this rocks. Yeah.
The question is, have you considered having a system that would be using different modules for different environments?
Yeah, so that means we reconfigure a single system so that it can be used either for fine sand, and then we reconfigure when we come to other approaches. No? Yes, part of. I mean, of course, we know that there are specialists for certain terrains, but if you take a look, for example, on the Sherpa system, this one can use just plain driving when you are on fine sand, yeah, and therefore it also has the swimless wheels with this browser, so it can walk drive very good over the sand. But as soon as we encounter really rocky terrain where actually just driving is not possible anymore, then you can switch to locomotion mode. You can use the legs for walking, yeah. Or maybe there are also then other terrains when you, for example, go very high inclinations. Then you would not just go driving like a car, but then there's also some kind of inchworming possible. So that means stretching out the front legs and then moving the back legs and so on. And so that you then have different kind of locomotion principles. This is, of course, also true for all the leg systems. We have different walking behaviors, as we also humans have. No? For example, we can go, when we go up a hill, we walk differently than we go on flat terrain. And so the systems provide a lot of possibilities.
Okay, thank you very much. Just one quick question from my side. Now that probably you knew that already, but having seen the previous presentation with the screw locomotion system, would you consider that in the future for the moon?
It really depends on the application. I mean, if you want to drill a hole or somewhere, then of course you wouldn't use of this concept here, but then the choice would be actually to go there with one of the system, and then we deploy a certain mole module that can go subsurface and can do analysis. I mean, I think from the pure exploration point of view, I can imagine that the system is maybe not so it's not so well suited to go over surface. No? So I think in terms of maneuverability, so that you can adapt more or less different speeds and directions, and you also have to consider you have to map all the environment around you. I think it's have some influences also on the choice of sensors that you can apply there. Yeah, that would be my question.
Thank you. There are other two questions that I think are relatively quick. One is about maintenance of the system. So the more complex the system is, more difficult to maintain, right? So what about maintenance in the moon, on the moon? Sorry.
Yeah, that's definitely a very good thing, and that's why we also have the choice to develop different kind of systems. As I said, they all have their pros and cons. So, for example, this passive suspension system of the Artemis is not so failure-prone like the active suspension system of the Sherpa. Yeah? So that means depending on what the robot has to do, you should always try to reduce the complexity as much as possible. Mm-hmm. But nevertheless, we're trying here to reach the border as what is possible here and to show on Earth what we can actually achieve. And I think if we show that we have here a very superior locomotion concept, which can, for example, reach the bottom of the crater, which another system just cannot reach with a simple locomotion system, then I think it's worth to develop more or to work more on the robustness of single systems, so that you don't have a high chance that a single system can break. And even if there is, try to use redundancy. For example, the 6-legged walking system I mean, if there one brake breaks, there's also high potential that you can lift it up and then locomote with 5 or 4 legs and keep on working.
Okay, so there's one last question also about maintenance somehow. So if the robot has some kind of malfunctioning during exploration, how do you plan to retract the malfunctioning robot to avoid space junk? I mean, to litter space.
Yeah, actually, this is not really on our primary focus, but I think in all the current missions, almost no system or there's not much an idea of taking the systems back to Earth. No? You try to get some samples back, yeah, but the whole system is actually not possible. It's even like this. For example, if we consider here this scenario to do this lava tube exploration, the actual mission behind this would be a 1-day lunar mission that corresponds to like 14 days on Earth. But that means you get out of the lander, you go to the crater rim, analyze everything, do the descent, and then use the remaining time, which is like then 1 or 2 days left, to explore the lava tube before actually the nighttime comes. Because if you then want to survive the nighttime, that also poses much more constraints on your systems. Yeah, then so you will leave some waste there, I guess, in almost every mission. That's currently the thing. Yeah.
Yeah, okay. Thank you very much again, Alexander, for your presentation and for your discussion. There will be more time, as I said, in the end for some other question.
Yeah.
So the next presentation is by Mathew Evans and Nick Castledine. Mathew received his bachelor degree in psychology and master degree in computational and system neuroscience, and as a PhD in robotics from the University of Sheffield. He has been working on biospinal robots and computational neuroscience at the University of Sheffield, the University of Manchester, and the University of Nottingham. Mathew is currently working on developing methods for robots localization and mapping in future sparse environments. While Nick is a research fellow in the design and fabrication of small inspection robots at the University of Leeds, he holds a master engineering degree in automotive engineering and previously worked for the oil and gas industry, developing subsea oil field equipment. He also worked as a research fellow developing a miniature inspection robot for 2-inch pipes to detect and classify radioactive contaminants. Mathew and Nick will talk about miniature robots for pervasive sensing in buried pipe. Matt and Nick, the floor is yours.
Thank you. Okay, so I'll begin. Great. Yeah, so we're from the Pipebots research project. So what the Pipebots project is about, so I'm going to play this video and turn the sound off, is about building robots to do pervasive sensing in buried pipes, so in water pipes and in sewer pipes. So just in the UK, there's something like 1.5 million road excavations a year to fix broken pipes, and it costs at least £5 billion per year to cause that. And you see the stats on the screen here. So part of the problem is that you don't know that leaks have happened until they've happened, so you can't do any kind of anticipation of leaking pipes, and also the accuracy of finding the faults is problematic because of the old records and no way of really identifying from inside the pipe where the leaks are. So the idea is to develop these miniature robots that can go into the pipes and monitor condition over time, anticipate failure, and then also identify the locations of those failures or potential failures more accurately, so the holes can be smaller and there's less disruption. So this is the sort of mock-up, and then the project itself is divided up into a number of research themes. So I'm working on the navigation theme, which is about localization and mapping. Nick is working on robotic systems, but we also have themes for developing novel sensors, particularly ultrasonic sensing technologies. We've also got people working on the communication and power problems within for the pipe environment, and then also teams looking at control strategies for sort of traversing the pipe network, but also for getting the robots around tricky obstacles within the pipes. So I'm going to talk about the localization and mapping, and Nick's going to talk about the locomotion. So our approach to this problem is taking existing localization and mapping methods and applying them where they can work in the pipe. We also want to exploit and incorporate prior map information, because we do know a lot about where the pipes are supposed to be and where the manholes are. And then the final thing is to use multi-robot cooperation. So the problem with simultaneous localization and mapping, which we work on, is sort of a chicken and egg problem. You want to build a map and you want to localize yourself within that map. So if you imagine you're moving from A through C to B in the map on the left, then when you get to B, you realize that that you're near where you were when you were at C, and then it can form it into a coherent map. So that's basically the process we want to go through for these robots within these pipes. But typically the way you solve this type of problem, and for some of these other projects where you have quite large robots, is similar to what's shown at the bottom here. Is this is the Stanley robot that won the DARPA Grand Challenge. So you have laser LiDAR sensors and lots of compute power, but we can't use that type of technology because the pipes are too small. Some of the diameters are only tens of centimeters across, and we want the robot to be a few centimeters across. So we don't have that sort of technology. And then the other problem that we have in the pipe is perceptual aliasing. So you can see on the right hand side, a lot of the pipes look the same regardless of where you are. These are all different locations. So there's that problem to crack. The prior information is wrong because some of these maps are 100 years old, especially in certain parts of the UK and in Europe. So they just aren't correct anymore. And then the GPS won't work underground, which is something that you could usually use for these sorts of things. So similar to the previous, or taking inspiration from some of the research that would have gone into the previous talk, we're focusing on visual odometry, which has been used on Mars rovers and other very difficult environments, impoverished environments, because cameras are small and cheap and robust. And you basically take a picture, you move the camera, you take another picture, and you can work out how the camera has moved with respect to the world by how the image has changed from one frame to the next. And so we've applied these visual SLAM methods to in live sewer pipes, data from live sewer pipes, in sort of preparation for when we get the data from the real robots. That's what I'm showing here. So this is just a video of, a video on the right-hand side of inside the pipe, extracting visual features, the green dots, and on the left, constructing a point cloud map in black, and then locating the camera within that map in the red points. So that's what we're doing. And just using this is a tool called algorithm called OrbSlam. So that's a widely used method in the field. And we're adapting it to our use case. The other thing we want to do, as I was mentioning, is we want to be able to use prior map information. So our PhD student Rob Worley's been working on the problem of when you're traveling within the pipe and you're going underneath a manhole, where the inspection is going to take place. And you know where the manholes are above ground, so you're able to correct any drift in the location. That's essentially what's happening here. You have the uncorrected trajectory in blue, and then the yellow dots are the known manhole locations. And on the right-hand side, we correct the black line, the trajectory, so that by the known manhole locations. The other thing we're working on is doing work in simulation. This is sort of slightly less interesting, but because we need to bridge the gap between the cameras that exist and the mobile robots that Nick's going to talk about. So this is just an example showing, I'll skip it in the interest of time. It's a similar type of thing as before, but now we have a simulated environment, and then we're simulating going into these manholes, detecting those, and then towards the end of the video, reconstructing a more complex network of pipes that reflects where the robot has been. We're developing these algorithms in anticipation of the robots that are going to be able to traverse these pipe networks in future that Nick's going to talk about now. So that's my bit. Nick, you're up.
Cheers, Matt. Thank you. If you could go on to the next slide, please. Nice one. Thank you. So yeah, I'm going to talk to you briefly about miniature pipe robot locomotion, mainly in the context of mobility within pipe networks, as that's what we're kind of designing for. But I imagine there'll be a fair bit of crossover in mobility challenges between manufactured pipes and kind of artificial pipes, which you'd probably see in a mine environment. So as Matt said, I'm part of the Theme 3 of PipeBots project, which develops miniature autonomous robotic platforms. So the primary focus of any locomotion system is to transport a payload, usually an array of sensors of some description around the pipe network. Unfortunately, there's no kind of one size fits all that's kind of suitable for all pipes. So usually there's some form of compromise dependent on the expected pipe environment. Some of the most common forms of existing pipe locomotion are kind of shown on the slide. The pig, screw, and inchworm styles rely quite heavily on the interface with the pipe wall, so it might not be suitable for environments where there's quite a large variation in pipe diameter, or kind of pipe networks with tight turns and junctions. The wheeled, tracked, and walking designs generally have more mobility around tight pipe networks, as they can turn on the spot and are less dependent on pipe diameter changes, but kind of might not be quite as suitable for pipes with high fluid flow levels and yeah, kind of like high flow rates, as they can be quite easily washed away. For any pipe locomotion style, one of the key challenges is kind of the miniaturization of the mechanical and the electrical systems, because you're kind of at the mercy of the limitations in actuator and motor sizes that are kind of available. The robot must also be robust enough to and reliable enough to survive for the mission length. So things like waterproofing and the ability to survive drops may be critical, depending on the type of pipe that you're operating within. So within the PipeBots project, as Matt said, we kind of focus on developing robots for sewer, water, and gas pipes down to a diameter of about 100 millimeters. So I'm going to give you a brief overview of a couple of the platforms that we've developed so far. If you could click on to the next slide, please, Matt. I think this video, yeah, it's playing. Okay. So the first of these platforms is called the Sprint Bot. It's given that name as it's developed over a month-long technical sprint to produce a robot platform combining technology from all the different themes. So this robot was shaped like a ball to allow it to be able to turn within the pipe, with wheels surrounding the body to reduce the chance of a robot beaching. It's also able to travel in pipes of 240 millimeter diameter and is fitted with an array of sensors, cameras, and speakers to allow the other parts of the project to use it for their work. And it also has the capability of being either tethered or battery powered. The building and the testing of the Sprint Bot kind of allowed us to collect highly useful data for future work to build upon in other areas of the project. Next slide, please, Matt. Thank you. So this led to the current design of the system. We've named the system the Possum system, likening it to marsupials carrying their young, with these small robots being the joeys in this analogy. There are three main components to these: the main chassis, which houses the mechanical components, the electronics tray, which supports all the circuitry and the sensor array, and the outer housing. These robots have a locomotion method known as WEGs, which are hybrid between wheels and legs, and allow the robot to step over larger obstacles than just wheels alone. But these could be replaced with just normal wheels or tracks if necessary, depending on the environments that you're operating within. These also have encoders fitted to the gear train to allow for speed and position control. And there's a custom electronics package, which allows us to utilize micro ROS, which is quite a compact and efficient way of controlling multiple robotic platforms. So the board is capable of communicating using Wi-Fi, Bluetooth, and OpenThread, depending on which is most suitable for the environment. And it has 3 time-of-flight sensors, which are mounted to front to provide a 90-degree LiDAR-like system for obstacle avoidance, and a small camera for SLAM. There's also internal IMU, microphone, and temperature sensor for additional sensing feedback to provide extra information on the surroundings and the kind of state of the joeys. Next slide, please, Matt. So one of the deployment concepts we've explored is using a commercially available robot dog acting as the possum or the mother robot. Actually, if you go on to the next slide, Matt, I think there's a video of this system in actually operating. So the intent is that the quadruped robot can transport the swarm of the smaller robots through a larger pipe or rough terrain, and then deploy the swarm to explore pipes of a smaller diameter. Traveling in a pipe with a curved surface is quite challenging, especially for something this small. Some of our colleagues within Theme 4 of PyBots have been working on control algorithms to assist with this task. The great reduction of size compared to the sprint bots allows us to have multiple platforms in a small section of pipe at the same time, which can move over and past each other. They also pose less of a risk of creating blockages and becoming stuck on certain pipe features. So you can see them in action. So yeah, once they've completed their mission, they then go back to the mother robot and they can be collected or back up and transported away. I think this is quite a long video, so in the interest of time, I'll probably move on to the next slide. Yeah, click forward. Yeah, so you can see them being collected up by the mother robot. So kind of future ways of further developing the mechanical aspects of the robots and kind of improving the locomotion. A few of the things we're looking at are features such as expandable legs, which would allow the legs to fold away within the body for like protection, and it would allow different ride heights depending on the kind of obstacles that we're going up against. In sewer systems, there's also quite large drops to connect different pipe networks. Therefore, designing a swarm that could remain fully operational after large falls would be beneficial. We've also been looking at quite an ambitious thing, giving each robot a mechanical interface to connect to other robots within the swarm to allow different maneuvers and allow them to overcome bigger obstacles together. So yeah, that's it from me. Thanks for listening, and I'll be happy to answer any questions.
Okay, thank you very much to Matthew and Nick for the very interesting presentation. So I have a couple of questions here on the chat. The first one is for Mathew. Which goes, in your animation, it seems that robots work like a swarm. If that's the case, is there a central control unit, or is there any other approach or option?
Yeah, it's an interesting question. It's still it's an active piece of the research in the project is how we're going to go about doing the sort of swarm aspects of, or the swarm aspects of the control and you know and the mapping. So at the moment, we've only been working on the single robot case, and then what Nick was showing with the sort of like mothership, delivering them, and then you know deploying the robots, and then they would have no coordination at that point. But you know, as I mentioned, we've got people working on the communication aspect and on control. So there are applications for doing more efficient searching of the network, and also and then if you can use the swarm, and also for using the swarm as for communication. So if you can only communicate over short distances, so you wouldn't have a centralized controller. You would have local robots working independently, but aware of their neighboring robots. So, because if you have a centralized controller controlling all the small robots, you're going to come into lots of communication problems. But the idea would be that the swarm of robots would be somewhat independent, but rely on the sort of mothership robot to come back and either for power or data transfer. So it's really it's a combination of the of like a hub robot and the smaller robots, which are independent in their own way. Don't know if that answered the question.
Thank you. Yeah, yes. So in the same line, there's another question again for Mathew. Since GPS doesn't work underground, of course, which technique have you found most successful inside the mine? And are there any detection limitation with that goes with the depth?
Right. So yeah, so we've been focusing on the cameras and images, and we've also done some work with acoustic localization. So if you do echo based localization, so they've worked quite well. We're looking into doing things with the LiDAR type sensors, small ones, time of flight sensors, but we haven't done that yet. So there's not the particular challenges of the pipe environment are not to do with the depth. It's more to the things that we found really challenging is actually newer pipes. So the older pipes are all right because they have lots of corrosion and basically stuff in them, so that there's lots of features that the images can like grab onto, and then you can work out how you're moving. If you go in a new pipe, which is really smooth, then it's much, much harder to do robust localization. So it's the condition of the pipe, and the worse the pipe is, the easier it is to localize, which is unusual, which is, maybe not ideal. It's good for us, but not in general. So yeah, that's where the particular challenges have come from.
Okay, thank you very much. Well, time for one last question for Nick this time. So the pipes need to be void, right? Or are the robots capable of moving against flows?
I'm sorry, say that again. I missed that.
So the question is, you ask if the pipes need to be empty, to be void, without water, or are the robots capable of moving against the flow of the water?
Yeah, good question. In the current state, they can probably get away with quite a low flow rate, as the ground clearance on the robots or the current iteration is quite low. So anything where the flow is kind of like hitting the level of the body, then it's probably going to be washed away. But we are kind of addressing that with future iterations. Again, with like the retractable leg mechanism, if we can bring the legs in and make it so that the body is naturally buoyant, it can maybe like go with the flow and reach other areas of the pipe, or it can find a way of like piling on top of each other and like creating a mass of robots so they don't get washed away, like locking together. Kind of different approaches for dealing with different flow rates. Okay.
Thank you very much, Matthew and Nick. There will be some more time at the end if there's more questions. Now we have to move on because we are slightly behind schedule. So our last presentation is by Santiago Martinez de la Casa. Santiago is PhD in Electrical, Electronic, and Automation Engineering from the University Carlos III de Madrid. He is associate professor and member of the Robotics Lab since 2005. And he has participated in more than 40 competitive research projects, both national and European. And his main research topics are construction robotics and humanoid robotics. He is technical coordinator of the European project Badger, and Santiago will talk about underground navigation and locomotion in this project, in the Badger project. So Santiago, the floor is yours.
Thank you very much, Claudio. I'm going to present some results about the underground navigation and locomotion with the Badger robot inside the Badger project and with the same name. So, sorry. Okay. This work was framed because of a Badger project and last year. This work was framed in this project, and the main objective of the Badger project was the development of an autonomous underground robotic system capable of the construction of subterranean tunnels with minimum disruption in the surface. For this purpose, this robotic system must be able to dream, navigate in the subsurface, and perceive its surrounding to avoid obstacles. The Badger underground robot is composed of 4 different modules: a drill head module, 2 service modules with the same function, 2 joints modules, and a wall support module. The drill head module integrates a drilling mechanism based on a rotatory drilling technologies to construct the borehole, and the joint modules provides the propulsion and the steering capacities of this robot. The service modules, including the robot, have a clamping mechanism which consists of airbags that inflate and deflate to fit the robot to the borehole. And the last module is the tunnel wall support. These modules sprays the walls of the drill bore with additive material to construct pipes for wall support. The motion of a badger is constrained by the tunnel that is being drilling. Badger cannot move sideways and must always move forward in the order to steal. So the robot cannot go in other direction and move forward and steal to steer to the top, to the bottom, left and right, but always forward. Our like motion is generated using the combinated operation of the clamping mechanism and the joint modules. Also, this clamping mechanism react the torque produced during the drilling. So they provide the force need to produce the advance of the robot and avoid as well the roll motion of the system. In order to perceive the obstacle that the robot can find during its movement, we present in the sensor we have 3 GPR antennas in the drill head with a field view of 120 degrees to the front. And they are installed in the diameter of the drill head, not in the front. The disposition of the antennas cover the 360 degrees of field, and we can view all the surroundings. A single measurement from the GPR, that is called an A-scan, can provide data about the distance of the antenna to the closest object that falls within the field of view of the sensor. In this work, in this presentation, we presented a solution of the slam problem for this robot. We want to determine the position of the drill head and simultaneously map the subsurface while the robot is drilling. For that purpose, we use the odometry estimations and the range of measurements from the 3 GPR systems. These GPR units does not provide a 10 sets of readings, just a 3 range with a big field of view. So the GPR range readings are grouped in different sets. The grouping of GPR scans process consists in gathering the range of measurements of the GPR ring and the odometry while the robot is moving. In the figure, we can see here the grouping process of 1 GPR is shown. The green arrows represent the displacement between 2 posts where the GPR measurements were taken. The range measurement at each post is represented by the pink cone. The displacement between 2 successive posts and the range measurements are stored. Without we have the data need to transfer these range measurements to the reference frame for each graph. Once we have two graphs of a scan, we can use them to correct the pose of the robot. The scan mathing method is used to estimate the displacement between 2 successive groups of scans. Given a reference group, a new group, and an initial guess of the displacement estimation between them, the objective of the scan matching methods is to obtain a better estimate of the real displacement. Our method combines 2 perpendicular 2D grid maps to estimate the motion of the drill head between two groups of scans. The vertical grid is used to estimate the displacement in the plane, x-seat, and the pitch rotation. And the horizontal one is used to estimate the xy displacement and the geo-rotation. For example, for a group of scan of 2D verticals grid that is shown in this figure, the probability of each cell of the grid represents the occupancy. Initially, all cells are assigned with an initial probability called prior. This probability is estimated using the log ODDS radius, a simple inverse model of the GPR. For the cells inside the field of view of each GPR scan, at distance between 0 and the neighborhood of the range, inverse models has a value smaller than the prior. In the neighborhood, it has a value bigger than the prior. So another 2D grid is created in a similar way for the current group of scans to estimate the relative displacement. The displacement is computed to maximize the probabilities at the cells of the grid of the last group of scans when inserted of the previous grid. Then here we can see both 2 degrees that are aligned after the scan matching process as shown in a darker color. So we can have the probability of all the space. Process is utilized in a particle filter to estimate the trajectory of the drill head of the robot and also estimate their surrounding maps, given the groups of a scan from the GPRs and the odometry. A set of potential trajectories that are considered by the particles, and the map associated to each particle is used in this filter. For performing the simulations that we made in the gazebo simulation, we select rods, gazebo simulation, and we implement 3 sonars simulating in this environment the GPR units. We can see in the picture an example of the resulting 3D octomap from the mapping. The simulated surface, while the robot moves in a straight line, is shown. The resulting map shows that the utilities perpendicular to the motion of the robot are represented with a low error. Also, the green we can see in the top picture, the green pipe, which is tilted in the simulated environment, is represented as a wider surface in the octomap. So we use all these probabilities inside the gazebo and the simulation problem in order to estimate these trajectories and to allow the robot move in the underground environment. We use the GPR information and use this data in order to perceive all the surrounding in the with an error in the front of the robot, because we don't have the GPR just in front of the robot. And the GPR sensors are located with in the radius of the drill head. So even with this allocation of the GPR in the simulation, we are able to allocate different piping systems estimate their positions and estimate and produce one path to allow the robot move in the underground with success. This was developed in simulation because of the pandemic. We were not, we couldn't test the system in the real underground conditions. And this is an non-working work. We are still working in this movement of the robot, this system, even after the finish of the project, the backyard project, because of the interest of some companies in developing this system. And this is all from my side. Thank you very much.
Thank
you have any question?
Thank you very much, Santiago. We have time for a few questions. I see 3 already. So the first one is, how do you extract the rock and the soil when it's excavated?
Yeah, we have a vacuum system with an industrial vacuum system that is attached to the robot. We have in the drill head, we gather the cuttings inside, and with this vacuum system, they are extracted and transported through a pipe, a tube, to the exterior.
Mm-hmm. Thank you. So next question is, how do you prevent the excavated tunnel from collapsing?
Yeah, one of the parts of the robot I mentioned in the first slide is like a 3D system to construct one tunnel to provide the wall support for the constructed tunnel. When the robot is moving, like this worm style, at the same time with this system in the back of the robot, we can construct the tunnel. We develop in the project two systems. One of them was tested with success during the project, and after finishing the project, we are developing a new system with the help of one company. Even the European project ended last year, but we are still continue working on this development.
Very good, thank you, Santiago. And the last question for you is, does the cutting head uses water for lubrication or for cooling? And if yes, how do you provide water to the cutting head?
It depends on the type of soil. Usually we don't use water. We try to not to use it. The robot drills on or is developed to drill in soft soils, and water is not necessary. But we have a system, a water system inside with a pipe and a pump, outside pipe. And if we need some water, we can provide it with an external pump.
Okay, thank you. So, okay, thank you very much, Santiago. There's no more question for you. Okay. Now there's moment. Is there any other question for any of the panelists? My colleagues, Victor. We have like 5 minutes for a couple of quick questions. No more questions. Okay. So thank you very much. There's more question. The webinar has come to its end. I would like to thank again all the attendees for the response. We have had more than 80 registered participants. And of course, I want to thank again all the panelists. Thank you, Jussi, Alexander, Matthew, Nick, and Santiago. Let me also thank Vitor, Anita, and Alberto from EFG for the organization of the event. And just a final reminder that the session has been recorded and will be edited and will be available on a YouTube channel of the project in the next few days. A presentation also might be available. We have to ask to the presenters. So thank you again for the participation, and keep following all the projects, in particular ours in the social media. So bye bye.